Welcome back to Historical Geology. I'm Robert Lopez, and I'm going to finish up Chapter 14 on Mesozoic history with the Laramide orogeny. So the Laramide orogeny was the final pulse of the Cordilleran orogeny, and it really went from late Cretaceous into early Tertiary time, 70 to about 40 million years ago. Again, we're seeing the shallowing of that Farallon plate, and we're really affecting areas or deforming areas farther to the east in the Rocky Mountains. New Mexico, Colorado, Wyoming, the Canadian Rockies, the Southern Rockies, the Sierra Madre Oriental, which is in Mexico. So it was kind of a wide-reaching event. This Laramide orogeny differed from the others in that first, there was deformation much farther inland, and there wasn't a whole lot of volcanism, although there is a volcanic field called the Absarica field that we'll talk about. So minor to no emplacement of plutons. And then also the deformation was vertical, so there seemed to be more of these uplifted fault-bounded blocks. Again, that's thin-skin deformation. And so the idea here is that the Laramide orogeny is that we had the approach of the Farallon plate, but somehow it was buoyed maybe by a mantle plume. That's one of the models. Another model is that as the mid-oceanic ridge got closer to the trench, so as we see the East Pacific rise getting closer to the trench, this is a young ocean lithosphere, less than 10 million years old. Ocean lithosphere really starts getting heavier and more dense than the asthenosphere after it's about 10 million years old. So when it's young, it's going to not want to subduct, right? So that's why it's being more shallow. And so here, what I have here as we're looking at this Eocene epoch about 45 million years ago, maybe that mantle plume is helping it from subducting. Maybe it starts breaking up farther east, and we see some asthenosphere make its way in there. And we do see some volcanics. In fact, I did mention there's the Absarica volcanic field that I'll talk about, which is over in Wyoming. I talked about how there's more of this uplift along these vertical faults, this Laramide deformation, where we're thrusting really Precambrian rock over Cretaceous and Mesozoic rocks. We'll talk about that. Really, we'll see that over in the Lewis Overthrust, which is over in Glacier National Park in Montana. Farallon plate moves nearly horizontal, so it's either a buoyant oceanic plateau. It's still young and warm because the East Pacific rise is really close to the trench. We see that a lot of the igneous activity ceased because the Farallon plate is not reaching that 100 kilometers, right? And so maybe the only way we're seeing volcanism if this plate starts breaking up along its path. So here we're seeing some breaking up, and we're seeing maybe some volcanism, maybe that Absarica field in Wyoming is being formed. In fact, some of these Absarica volcanics actually have little xenoliths, fragments of oceanic lithosphere that they brought up, little xenoliths that were brought up during the eruption. So again, here we're looking at the border between Montana, Wyoming, a little bit of Idaho down here. So there's Idaho, Montana, Wyoming. And we're seeing the Absarica volcanic group in two different phases here near Yellowstone National Park. I talked about that overthrust. Another word we use for an overthrust is a French word, which is décollement. So the décollement is one of these thin-skinned, shallow-angle reverse faults or thrust faults. In fact, that's the definition of a thrust fault, is that it's usually less than 30-degree angle. So a décollement, and you see quite a bit of displacement. So the Lewis Overthrust, here we're taking Precambrian limestones and shales, and we're thrusting them over the top of Cretaceous rock, right? So we have Chief Mountain here on the east, and toward the west we have some other strata. Looking at this here, this is the Precambrian rock that overlies that Cretaceous rock. And then Chief Mountain is a limestone block with a little bit of shale on top. And at the base of that is that Lewis thrust or the décollement. And so here is another picture showing that Lewis décollement. And then this Precambrian rock, this formation, this limestone sitting up on top. I do have it on Google Earth. So here's Chief Mountain. So we're looking from high altitude, looking out towards the west. So here's Washington and Oregon. And we're going to look at basically the front range here as we go from Alberta, Saskatchewan, Montana into the northern Rocky or Canadian Rocky Mountains here. So we zoom in, we start seeing those white rocks, which are those Precambrian limestones. There's Chief Mountain, so we can get a better view of it. And so here we're seeing right along the base here, all these are those Cretaceous rocks, and then these are the Precambrian rocks. And so basically all along here is that Lewis overthrust, or that décollement, which is thrusting these rocks over the top. Now looking at some of the Mesozoic sedimentation, which the Colorado Plateau is famous for, again, if you go to Utah, where we're seeing these classic sandstones. In fact, the Navajo sandstone is famous in Zion National Park. So Zion, most of it, and the Navajo sandstone is really a cross-bedded sandstone, really huge cross-beds. But if we start off with this Paleozoic Kaibab Formation, so that's really Permian, and this is the topmost unit you see in the Grand Canyon. And then after the Permian, we're going to enter the Triassic, and one formation your book talks about is this Moenkopi Formation, which is a series of shales and some stream deposits. And then we have this unconformity with this conglomerate, Shinarump conglomerate over the top. And then there's this famous Chinle Formation, and there's a little excerpt in your book that talks about how the Chinle Formation is famous for its petrified trees. And so there's lots of petrified trees. I'll talk about that in a moment. Then we have the Wingate Sandstone, which is Lower Jurassic. Note that the Assic Sandstone over by Las Vegas, and also in California, we have some Assic Sandstone. That's about the same age, Lower Jurassic. Then there's a Kayenta Formation. And then we start seeing, in the Upper Jurassic, we start seeing the Navajo Sandstone and the San Rafael Group, and we see the Sundance Formation. And finally, we get in the Upper Jurassic, we start seeing the world-famous Morrison Formation, which is famous for the dinosaur bones that we find there. This is over near Sundance, Wyoming, kind of the northeastern part of Wyoming. And here we're seeing some of that formation. So here the Morrison is the Jurassic, and you see the Sundance sits right below it. And the Sundance is famous for a pterosaur, which are, pterosaurs are, they're not dinosaurs, they're flying reptiles, but they clearly leave these trackways. You can see the trackways along these shorelines. See, they're all ripple marks. So this was an ancient shoreline, which is now tilted. But these pterosaurs were walking along, probably looking for fish or feeding right along the shores of some Jurassic seaway here, of the Jurassic Sundance Sea. And then when we go and look at the Navajo Sandstone, again, huge crossbeds telling us that they're windblown Aeolian crossbeds. And then the famous Morrison Formation, which are stream deposits, and really material being eroded off of the Antler and Sonoma highlands off to the west. And these are river deposits, and there were floods, and there were meandering streams, and you see all these dinosaur bone beds. These are all Jurassic dinosaurs. There's sauropods in here, Launic dinosaurs, and they were washed up along the riverbank, so there was periodic flooding. Here's our petrified trees from the Chinle Formation. Then there's a section in your book that talks about how these accreted terrains are important. So remember, they're small, exotic. In other words, they formed someplace else and have been attached to North America. They've been accreted onto the larger continental blocks. And there's several of them. There's several in the Sierra Nevada. There's the Klamath Mountains. There's several in Oregon that are not shown in here as well. They differ from each other in terms of their fossil content, their stratigraphy, their structural trends, their paleomagnetic properties, because they're forming in different parts of the Pacific Ocean and then all being attached to California. We talked a little bit about the McCloud fauna and how it's related to maybe more northerly or colder waters, maybe waters off of Alaska up over here and then somehow brought to California. And so they have pretty distinctive corals and fusulinids and some brachiopods. And then, remember, this is famous for the eastern Klamath terrain, and some of the northern Sierra terrain. Shoofly complex also has these. And then we talked about the Tethyan fauna, which has their own characteristic fusulinids and corals and brachiopods. And these seem to be more equatorial, maybe more of an affinity with China or Japan. And here's a map showing some of these McCloud fauna, which is a darker features, and then the Tethyan fauna, which is kind of this stipple pattern. So you can see that the foothills terrain in the Sierra Nevada and then the western Klamath terrain also has this Tethyan fauna here in California. And then as we go along, a famous formation in Northern California, the Husselkus limestone, is that it's a Triassic limestone, and there was in 1905, 1910, they found fossils of an ichthyosaur. So ichthyosaurs are marine reptiles, and these marine reptiles populated the Tethys Ocean. In this case, well, we're looking at Triassic, we still have the Panthalasus Ocean, but there's an affinity between organisms we see in the Tethys Oceans and then ones we see here in the western United States. So we have these Triassic Shastasaurus fossils. And earlier I mentioned that as much as 25% of western North America is composed of these accreted terrains.